Hello guys, welcome to this comprehensive CFX course. Whether you are a beginner or advanced CFD user, this course series, this video series will help you a lot. Myself is Muhammad Irfan and I have a 5 year of experience doing CFD and design projects. In my journey, I have completed more than 200 simulation projects. It is a complete CFX series in which we will cover all of the advanced and basic concepts. We will start with some of the basic user interface and basic simulation settings, and then we will dive into the complex simulations like the turbo machinery, multi-phase flow, and discrete phase analysis. So in today's video, we are going to analyze a static mixer which is being used to mix up the cold water with the hot water. So it is a very basic physics analysis. There is no complexities, but by doing this analysis, you will learn a lot about the user interface and the basic setting of the CFX and ANSYS Workbench. So let's start. So if we see the problem overview, there are two boundary inlets, one for the hot and one for the in, and there is one outlet. So water enter the hot inlet at 2 meter per second and the temperature is 315 Kelvin, and at the cold inlet water enter at 285 Kelvin and with the same velocity 2 meter per second. Also the size of the hot inlet and cold inlet is the same. So what we are going to learn in this tutorial, we will see how to run a basic simulation in the ANSYS CFX and how to set up the thermal mathematics in the ANSYS CFX, getting the results, and then we will see some of the tactics to build up better mesh. So let's start. We can do the analysis by opening the workbench, or we can go to the CFX app directly. So let's see the difference in both of them. So once you have opened the workbench, you have to see the toolbox and drag and drop ANSYS CFX. So if you open the CFX directly, what will be the difference? You can see you should have a geometry and meshing at the start, but Workbench provides you a easy access to all of these things. Like I can define the geometry, I can do the meshing, and then the setup and solutions. So I do not have to open multiple applications. But the disadvantage of the Workbench, it takes more memory as compared to the CFX application. We are going to use the Workbench to handle all of the things in a single window. So let's start with the geometry. I am going to import a geometry that I have built in the SolidWorks. I am using this step format. You can also use the parasolid format or STL format. Also is also acceptable with this space claim. So let's come to the meshing. After importing the geometry, I will provide the source file of the geometry in the video description. So let's start with the default setting and generate the mesh. So if we see the element quality, it's good, and the aspect ratio is also within the given range, so it should not exceed the 10 to have better results. Okay. I am going to add adaptive sizing here for the initial results. So let's set it to 3 and generate it again. So you can see there is a little bit problem with the meshing here. The cells are not accurately generated. So insert face meshing here to see if this will work. and yes, also at this stage add face meshing. Okay, so we have better meshing now. You can see we have captured the circular faces more accurately. Now let's decrease the mesh size to, you can say, 5 mm and generate the, we have total cells of 1,72,000 approximately. Also if we see the aspect ratio, it's good. So after doing the meshing, the next step is to define the boundary conditions. So we have hot inlet, we have cold inlet, we have outlet, okay, hot inlet, outlet and cold inlet. Okay, after defining the boundary conditions, click on the update. So the meshing is updated in the workbench. Now come to the CFX setup. One of the important thing is that before proceeding to your projects, please save the setup. So in case if the software crashes or any other thing happen, you should have the backup. So I name it CFX mixing tank. Okay. Mixing files and okay. And after doing each of this step, I recommend you to save the project. So sometime, especially if you are using the student version or unlicensed version, so software crashes a lot. So in case of if the software crashes, you should have the backup of your data. So now let's define the setting in the CFX tree. So if we talk about the user interface of the CFX, here is the tree window where you can see the different settings. Like first of all, I have to define the boundaries conditions, analysis type, which we can choose the steady or transient, and then we have to define the domains and the fluids or solids in the domain sections, inlet and outlet boundary conditions or wall boundary conditions, whatever we have in our analysis. Then if there is any interfaces between solid and liquid or liquid to liquid interface, we have to define it here. So then after defining the flow analysis setting, we have to come to the solver setting. So we have up to this interfaces, we have defined the physical setup. After that, we have to define the mathematical setup, like what will be the solution units of the solution, the control in the solver, and the output control, what values we need at the output, or if we want to monitor any of the thing, we have to define here. We will study it in detail. Okay, after that there are some other things like coordinate frames. If I have to define some new coordinate system to have some value against it, we can define it here, or some kind of user locations, material settings. I can add up new material from here, or I can use the predefined library materials. Also, if we are going to study the species transport, we can define the reactions too, like in the combustion or any bioreactor. If there are some kind of reaction, we can define it from here. These are the things we will study out in this course journey, inshallah. So also, if we talk about the graphical window here, you can see if I have to rotate it freely, I can have to locate my cursor at the center, and I can rotate it in the any direction. Or if I want to rotate it around any specific axis, so I have to go to the corners. So now if we go to these corners or this corner, any of the corner, we can rotate the model about the y-axis. So you can see I can rotate it about the y-axis. And if we go to the center at the end of the center, in the center at the end of the window, I can rotate it about the z-axis. And if I go to at the corner a little bit inner side, I can rotate it about the x-axis. You can see it, I can rotate it about x-axis now. So this is how the things work. If I want to again want to make it to the isometric view, I simply click on this dot and it will go to the isometric view. Also, if I want to drag the component to some location, I can use the pen command. If I again want to see the fit view, I just click here and it will reset the geometry. So let's start with the setting. I am going to delete the default domain. Let's just insert the domain, fluid domain, and location. We have only one domain in this case, and the material, we have to select a material of the domain, so we have to use the water for the current simulation, so it is predefined. Also, if I click here, I can see some of the other materials. So I can use them too. For this case, I need water. Okay, click on OK, and now we have the define the material. Also, we have to apply the gravity, so we have to use the buoyancy model. Define the gravity in the desired direction. In our case, the gravity is being applied in the y direction, negative y. So I have to define the gravity. So our reference temperature is 285 Kelvin. Okay. In the fluid model, we can use the shear stress transport or K epsilon model. I will use the K epsilon and thermal energy model. Click on OK. Now go to the insert boundary condition, cold inlet. Okay. If we see the boundary is here, the speed of the flow is 2 meter per second and 285 Kelvin. 285 and 2 meter per second. Click on OK. Now again go to insert boundary, hot inlet. Click on hot inlet. We have selected the location. Now go to the boundary conditions, boundary details, and the speed is 2 meter per second. The temperature of the hot inlet is 315 Kelvin. Now we have to define the outlet. If the name of your location match with the boundary type, it will automatically select the boundary. Now the relative pressure is 0 Pascal. Click on OK. Now come to solver control. I am going to use upwind for this simulation. Upwind provide us fast results, but it is not accurate model, and for the final simulation in which you want to see the detailed results of your simulation, I highly recommend to not use this model. In that case, you can use high resolution or specified blend factor. I am using upwind for the fast simulation results. So max iteration, I am going to define 450, and the convergence criteria is 1 e to the power minus 4. So that's all. If we set it to minimum iterations, set it to 50 and click on OK. Also in the output solver monitor, temperature, so this you can see. For this I have to define the coordinate frame, insert, click on outlet and OK. Now go back to the output, click on chord 1. So we will see the results of temperature at the center of the outlet. Click on OK, close this window, save the project, and now come to the solution. Okay, so in the result definition we are going to use double precision. Also I am going to use also I am going to use the local parallel processing. So I can define the number of processors. It depends of your laptop or computer model. I can use 12 of the processor in my case, but I'm going to use only 10. The initial values should be initial conditions. Okay, start run. So here is the user points. You can see the monitor point where I have defined the temperature value at the outlet center. So he's providing the temperature value at that. So by doing the defining the monitors, we can see some of the results while doing the simulation, if we are getting the desired value or not, and also the how the solution is being converged for that point. So you can see the first the temperature goes down and then it goes up again. So we get the converged solution. So now let's close this window and go to the result sections. So in the result section we will define to run in the result section we will learn to define how to create points and streamlines, and how to change the coloring scheme, create contours, and slice the planes. So let's start. So first of all, I am going to define a location by creating a slice in the domain. Click on apply, but I need a plane in the ZX. So at the 0. So when we have created the slice, now we can go to the color scheme. If I click on the variable, so we have the variable section where I can define different variables I have selected for the simulation results. So first let's see the temperature mixing. Click on local and okay, click on apply. So you can see if I go to viewer option and click on the axis visibility, so now we can easily handle the, now we have to turn it a little bit, no, it's fine. Also I want to change the style of the legend, so come to the tree and click on edit. I want to make it horizontal first of all, and then I want to make it general instead of scientific. So decrease the precision to or 1. So now come back to the plane and let's change the coloring scheme. Let's select the BGR modern. So see the colors are being changed. If I go to the some of the, like you want to see black and white cells, so I can select the grayscale. So the benefit is that the points of interactions are more visible in this scheme. You can see that. So also I can define the size properties by going to this contour section, click on OK, click on temperature, location, select location, which is plane 1, and click on OK. So you can see the results here. Also, if I increase the values of contours to 150, so you will see a more refined results. Also, we can edit the legend again because the values are being mixed with each other. Sorry, the values are being mixed with each other. Okay, now it's fine. Also, we can see the vector plot. Let me select the hot inlet. You can see the results here. Also, if I want to change the location to plane 1, so you can see it provides us the knowledge about the vorticity and how the particles of the fluid are being moved. So let me change the variable to, no, we do not have option here. So let's define the streamline to see the view. Let me start with the chord inlet, and let me decrease the number of lines to 10, or we can decrease it to 5. Okay, now let's duplicate it. Go to streamline 2, click on hot inlet, and then change the type of the streamline from line to ribbon. Click on apply, or we can select these. Let me decrease the number of streamline to 2 also from here. Okay, now look, we have better understanding. Also, I want to change the color scheme to temperature. So you can see it here. Now we can also create a small animation of the streamline. If I click on the animation button, click both of the streamline and click on OK. So you can see the flow pattern, that how the flow from the cold inlet and hot inlet is going through the mixer and then going to the outlet. Okay, one of the more results you can define, like for the fluid walls, I can also see it in some of the color, like the temperature of the fluid wall, sorry, the mixer wall. Click on OK. So you can see how the fluid is flowing around the walls. Also, I can change the transparency. Let's click on 0.5 and also show the, so you can see the temperature at the boundaries of the wall and inside the domain. Let me increase it to 0.7 so we have better understanding. So you can see it here. So let's come to the mathematical results that we can define from here. Let me click on the mass flow average and click on the location outlet. I want to see the average temperature at the outlet, so click on temperature and click on calculate. So we have the value of 299 point, almost approximately 300 Kelvin at the outlet. So after that we can also see some of the expression. यहाँ से भी काटना यार. So let's come to the final point of this analysis, how to define the expressions in the CFD post. So come here and click on the expression button. I want to see the difference in temperature. Click on OK button, and now go to functions, CFD post, mass flow average. From we have to define temperature under this bracket. Click on OK temperature. Also we have to define the location, so I am again right clicking and come to location. You have to select the outlet. Sorry, I have done a mistake. The function, I have to define the max value, not fine, minus minimum value of the temperature at the outlet. Okay, click on apply. So we have the temperature difference of 123,709 Kelvin. Let's come back to the graphical window and click on outlet. Change the coloring scheme to variable. Click on temperature and click on local. Click apply. So you can see the difference. The flow coming from the hot inlet is a little bit hot as compared to the flow coming from the cold inlet. Okay, so after doing the CFD pose, close the window and then press Ctrl S to save the project. Let's come to the next point, which was the building a refined mesh and how to save the time in the simulation. Here we have done the comparative study of hexadominant meshing and triangular meshing. So you can see the number of elements in the hexadominant meshing is 1 lakh and approximately 15,000. In the case of triangular meshing, the number of elements are 2 lakhs and 35,000 approximately. So if we see the quality of the meshing, you can see that the aspect ratio is very high in some of the cell in case of the hexadominant meshing, but the aspect ratio is fine in the case of triangular meshing. So for the element quality is low for the hexadominant meshing, but we have very good quality meshing in the triangular meshing. But if we come to the residual, you can see the residual scheme. This is I think I have changed the one second. Yes, and for the solution display monitors, you can see here. So these are both of the results. If I talk about the first one, we have hexadominant meshing in this case, you can see here. And the quality of the meshing, sorry, I have done the mistake, exactly I have done the mistakes in the while making these slides. It is for triangular meshing and it is for the hexadominant meshing. If I show you the solution monitors, so you can see a very refined or a converged results we get in this case. But if we see the second meshing, which is triangular, we have almost double mesh cells in comparison to the hexadominant meshing. And if we see the solution monitors, the solution is being run for 300 iterations and still we do not get the converged solution. And also there are a lot of disturbance, like the fluctuation in the solution, which is not a good sign. So to have a better solution, the solution should go this like this. The monitors should gradually decrease with the time, and there is no significant disturbance with time. So you can see it here. So both of these simulations are being run for the 300, but you can see the difference between the results. The simulation is being run on the high resolution, not the upwind scheme, so that's why the convergence take place lately is in comparison to the other solution. So why I am talking about this, you can see I just created hexadominant meshing in this case and provide the same edge sizing to both of the schemes. You can see I just suppress the hexadominant meshing and provide the same sizes to the meshing. So in the number of elements are almost 1.7 to 1.8 times more in comparison, or sometimes it is more than double in comparison to the hexadominant meshing. But still we get better results with the hexadominant meshing and fast solution. So I always prefer to build up the hexadominant meshing until unless it is not working. So that's for the today's session. I hope you have learned a lot of new things. In the next session we will do the parametric study using the ANSYS CFX.